Yeah, thanks for coming. So today we are very happy to have Hong Zhang, also known as Kilar Zhang, from Shanghai University to tell us about his a series of work he has done recently. So title is like string duality and the compact stars. So let me brief introduce Kilar. So he got his bachelor degree from Tsinghua University and then moved to the Tokyo University for his PhD study. And now he is holding like this associate professor in Shanghai University. Okay, that's welcome.
Thanks a lot for the introduction, and also thanks a lot for your kind invitation. So I'm very glad to be here to present my recent works on string dualities and compact stars. This is mainly based on some works with my students and with my colleagues and also with my friends. Yeah. So yeah, including the 3 papers this year about the string theory and proof of AGT conjecture, and also the duality between Seiberg-Witten theory black holes, and also some this is like applying this ADS QCD to neutron star equation state, and also like not working so okay. Also like 2 papers out of the 5 ones last year. So also some 4D AGT conjecture proof and also some Seiberg-Witten co-duality to black hole stuff. Okay. So yeah, those are my students, and so my works basically they focused. Sorry, those are written in Chinese, but anyway, we can read the picture. So on focus on kind of gravity. So we say recently we have this gravitational waves observations, and also like string theory is known is supposed to be a candidate for this kind of quantized gravity theory. So years ago, I mainly focused on this side, like on some quantum algebras and this AGT conjecture. And also, when I was for the undergraduate study, I majored in nuclear physics. And recently, since the observation of gravitational waves, we found many new ways to observe those kind of black holes, neutron stars, and also some possible dark stars made by dark matter, or some possible like mixed star or hybrid star between neutrons and made by neutrons and dark matter. So we interestingly, especially the 2 or 3 years, like we found people found some duality between this kind of different series. So we found that, for example, for this is like initiated in like 2020 or 2021. Like the group from Italy and Japan, they found like there's a duality between this so-called Seiberg-Witten curve in the gauge theory side and to the black hole Quasinormal mode. That means like the Quasinormal mode in black holes, it was once only could be calculated numerically, and that's very important to infer the phase in the gravitational waves study. But through this duality, we could using this Seiberg-Witten curve knowledge, and that's also linked to this AGT conjecture, that we could start from the instanton counting or because of potential functions. That is like analytically we could find the frequencies in the black hole side. It's linked by the reason why they could be done that way is they are linked by a common this kind of so-called Horn type equation. So you could like find the link between. And also for we will introduce delve into the details later. And also there's some other dualities like this kind of so-called ADS QCD duality. And applying this, we could find like especially we could using the string theory constructions from the brain constructions to derive the equation states satisfied by like neutrons and or you say like by hadrons. Why that is more important? Because like for neutron stars, we know the density is quite high, and this cannot be easily achieved by this kind of normal productive calculation or any experiments on Earth. So in that case, we need to derive this equilibrium state theoretically, but this duality offers us a new way and an efficient way to calculate this theoretically. And this could also this is a very important parameter to affect the waveform pattern of the gravitational wave observation. All in the country, actually we start from this kind of observation, and we want to constrain the window of this equilibrium state. And if we could derive that numerically, that will be very important to do this, because currently all those mainstream equilibrium states, they are like phenomenologically derived, or like you say, like not theoretically stuff. So that's one thing very important. And also on this side itself, like the AGT conjecture itself is a duality. It's between this 4D gauge theory and 2D conformal field theory. And so we are also working on some proof of this conjecture. In some simple cases, this is proved, but for the general case, still like work need to be done. And if I have time, I will like further talk something about the dark matter and dark star, but that will not be currently. It's not directly linked to the string theory. So maybe in the future, I'm not sure. But anyway, let's go to the details later. Want to go to the. So for maybe many of you are already familiar with the main idea with this kind of AGT conjecture. So it's basically the relation between this n equals 2 supersymmetric gauge theory in 4 dimension, and also the it's like linked to the 2-dimensional conformal field theory. So the partition function of the 4D side is supposed to be linked to be identified with the correlation function, the 2D safety side. So this is called the AGT conjecture. The mainly is because of the one loop part in this partition function, it's already known to be connected to the 3-point functions of this 2D side. And in the original paper with this Ade Gayotto Tachikawa paper, they found like for the SU2 case, there's a duality between this instanton part of this conformal blocks on this safety side. So this is in the original paper, they checked by instanton expansion, and also later it's like generalized to like SUN case. And actually, there are many other applications and generalizations. For example, this could be lifted to 5D, and this will go to q-deformed CFT. And also, you could even have 6D gauge theory, and then you have elliptic deformed like still 2D conformal field theory. Every time you if you go to 5D, you have one more parameter, and then now you have q-deformed, so it's still one more parameter. This q is like linked to the radius of this extra dimension, which is like a periodical dimension. So there are several ways, two mainstream methods to trying to prove this AGT conjecture. So first is like this kind of like direct approach. It's initiated by like Mirosov and their colleagues. So the direct approach just start from the 2-dimensional conformal blocks, and then there's a way to rewrite those stuff into the so-called Dosenko-Fatigu integral. And this integral mathematically are in a form of the so-called Seiberg integral form. And the integrand can be transformed into the Jack polynomials. And then if one could show that this form is equal to this instanton part of the partition function, then it could be proved. The thing for this approach is that if we want to do this, it could only be done easily for beta is 1 case. So what is beta is 1 is like beta is like for the Nickel partition function, there's some omega background. It's like the deformation of the matrix, and the parameter epsilon1 and epsilon2. So beta is just minus epsilon1 over epsilon2. So when this beta is 1, it's like called like it's a simplified case. So under that case, like there are two parts will be simplified. First, this jack polynomials will be simplified, reduced to the so-called Schur polynomials. That is easier than this jack polynomial. And also for beta equals 1, there's one more important stuff. Like um, the other thing is like this equivalence is termwise that I will show you later. Like the other simplification when I introduce some more details. There's also another recursive approach. That means like you could like add some operators inside and try to find like say wide identity, and then you could have a side proof of this kind of AJT conjecture. But this cannot serve as a full proof. But although it's like this works for aperture beta, but it's very useful. But it's still like we need to because this only gives you some constraints, but it will be very inspiring for like for which could lead us to the full proof later. So let's go back to the direct approach. So this is like how they found a ecological partition function, and with this background and this omega deformation. So we need to introduce this kind of Young diagrams, which is like way partition. Anyway, many of you are working on this quantum algebra and the mathematical physics. You are very familiar with this Young diagram, and so especially this like in central part of this partition function could be written as an expansion of this instanton. This Q stands for the instanton, and this Y is like just the different Young diagrams. So you will have a sum like between different Young diagrams. You start from 0 boxes, and then the 1 box and 2 box, like it depends on how many, how big Young diagram is, and then yeah, so there's some details which we could omit, but anyways, like you have some explicit form written in terms of the sum or like multiplications of this Young diagram terms. And also this for the single gauge group and for linear quiver case, like you have a similar result. So the AJT conjecture claims that like for the this is for the SU2 case, for which it's linked to 2D CFT. It gives you a Lewis theory, like 4-point function, 4-point correlation function will like this could be written in a form like this, and this one it's actually like you could be calculated by this so-called like conformal block, and these positions could be placed to like you could fix 3 of the positions using the CFT symmetry, and of course we could have a SUN generalization that you will have the case for the polar field theory, and then yeah, this is just some polar field theory. Then we will encounter this W algebra stuff. I will not give too much about the details. I'll just show the main story. So for that case, like the 4-point function or multi-point function would be this is mainly the 4-point function case. You could add some screening operators inside, and then that will give you some Dovzhenko-Fatipoul integral, and we just use Wick's theorem, and then it looks like some complicated form, but actually they could be rewritten using the so-called Seiberg integral. And this integral is like it's actually related to also this Caruso-Sutherland like Hamiltonian stuff. And if you are working on quantum algebra, you may have encountered this before. So yeah, actually for the simple case, when this kappa is 1, it's just the Euro beta integral, so this is more familiar. And it also has this AN extension, or which link to SU1, you just have some more cross terms inside.
Just maybe a good precision in the previous slide, and that is the Zhang formula. This screening charge form is pretty specific, right?
Right. The screening charge is like why you take from here to here. Like there are several ways to take the contour.
Exactly.
Yeah.
But also analytically, there are some conflicts.
Yeah. There's some ambiguity of taking this contour and taking the relation.
Right.
So there's some they just choose one. And actually, especially for the proof later, especially for mathematicians, it's very important to take in different contours. Very good question. Thank you. So for in that case, we could actually using this Seiberg integral, the Dothenko-Fativo integral could be written in terms of this Seiberg integral form, and it's really like we it's probably for what? For the beta is 1, like the contour need to be altered a bit, like so. Yeah, that's like we need to define some contour, complex contour, like because when beta is 1, like some of the contour like defined before, they just will not work. So you have to define some new contour here for beta is 1, and so in that case, we could just rewrite this Dothenko-Fativo integral in terms of this. This means like the Seiberg integral, and inside the integrand just becomes this Jack polynomials, and this is the Seiberg average.
Sorry, can you recap in which case you said that you will be having like a stack of Schur polynomials instead of Jack?
Yeah, just for beta is 1.
The square of the van der Waals for beta equal 1. That is just the measure of the symmetry.
Yes, I know. The beta 1 is also an integrable case. Beta half to beta 1.
Because the symmetry group.
So that's exactly where reduction happens.
That is representation of the group and the issue.
Yeah. The beta is 1 like makes things clear, easier for two sides. First, like for the Schur, Jack polynomials become Schur, and also this for this kind of integral, you have beta here. This will reduce to 1. This like will reduce to 2. So this also
just a precision. So it's canonical.
Yeah. And right. Inside why we could like have this Jack polynomials integrand inside is like because we are using this Cauchy-Stanley identity that we actually start from some power sum, and then this will lead you to some Jack polynomials, and this exponential beta
representations of something. The labella.
This one.
In this, the labeling. It is a block. I mean a young.
Yeah. Why is the young?
So R stands for young.
R is also young. Sorry, like so sorry for the notation. Yes, this is also Y here. It's probably on the when I'm making this string theory size, I'm always like not very good at making this. But later maybe the great compact star part is better. Anyway, right, as we mentioned before, like we want to start from this Dothenko-Fativo integral, and then there's something inside here, and this kind of stuff will later be transformed using this kind of like not just that, but also some other stuff. You will have this power sum and then end up with some Jack polynomials inside. And of course, for beta is 1, you will have like this Schur polynomials inside. So yes, it's some introduction of the Jack polynomials that is actually the aggregate function of this correspondence Hamiltonian written like this. And right, it's some low levels it could be anyway. Any level you could write them out, but right, it will become more and more complicated. And for the Schur functions, the definition is easier. Like of course, it's also some simplified this kind of Cauchy-Sutherland Hamiltonian with beta is 1. But you could also derive from here this kind of determinant of this kind of matrix with some fundamental downstairs. So here we need some to proceed with our calculation. We need this kind of integration formula, and maybe in the slides before you have noticed that for SU2 case, it's already done like 14 years ago by Milov and his friends, colleagues, and 1 year later in in 2011, that's also like 13 years ago, we did a paper for this SU1 case proof. But at that time, we don't have a rigorous like formula for this. We only have a conjecture. Then 10 years later, those are mathematicians in Australia, and right, we have already rise to each other like more than 10 years ago, and it's for Brafadavana, they find a new they have proved that rigorous formula for this one. And also at that year, like this first author, Albion contacted me by email, and he said like we have proved this formula, so maybe useful to you. But also like in that paper, they mentioned that our conjecture was not precise. So that's kind of embarrassing because like it's like actually that was my first paper, and we had this kind of conjecture on that, and then we have some checks, and then that could be used to the proof of AGT conjecture for beta is 1. But then at the time I wanted to check immediately, but unfortunately at the time I was mainly working on some gravitational wave studies like in Taiwan province, so it's kind of busy. So until later, when I just joined this Shanghai University 1 year later, so I have more friends and I have more time, so I just also work together with my friends to check like whether my conjecture was wrong or not. And then it turns out that although it looks very different, but actually their rigorous proof is actually exactly the same as our conjecture made 10 years ago. So it's just the form looks very different. But of course, to be more precise, like they have defined a more concrete like this kind of contour that of course we did not consider about the contour before because we did not do the integration 10 years ago, but so they did that integration, and that is like yeah, at the time like we have this kind of conjecture, but this is actually the same as the previous one. So with this conjecture, then we could find like this integration actually could be written in this way, and when we successfully write that into this way, it's actually linked to using some complicated lemmas. We can show that they are linked to the neutron Palich function on the gate side. So this is the 4D case. Like we have the for proof for beta is 1 now. And so you may wonder like why this like general beta case is difficult. So one of the main reasons, not just because like we need to do the calculation, we need to calculate this jackpot amount by ourselves. That could be done, but there's another thing which is not so easy because like we need a sum here. You see, let's go this side. Go back. Okay, right. We need taking a sum of this Young diagram for the 4 incidental Palich function. And for beta is 1 case, like this is on the gate side, and on the safety side, we also have something like this kind of incidental Palich function. But in that case, this q is the position. Remember, for the 4 points, we have the fixed 3 found to be 0, 1, infinity, and the other is q. the Q is just the same as could be identified with this Q of this, which is for the instantons. So on the safety side, we also have this expansion. But for beta is one case, it's like the equality is termwise. That means that for each y, we will have this n is like how is equal to its counterpart on the safety side. But for general beta, like we need to take this sum first. For example, like for if you have two boxes, like two possibilities, like you have two boxes. Oh, you have very nice talk. Okay, so right, you could this way or this way, right? So two boxes, you could have two possibilities. And so even for the two boxes case, like you need to sum these two together to cancel the poles. Then you finally end up with a equality. So that is makes you very difficult to directly to do this kind of equality. Okay.
It's a generic beta.
Right. So for the general beta, they also Mills they have like encountered an idea that you could they could like use something called so-called the generalized Jack polynomials, which means like they start from this kind of definition, and here is like the Jack polynomials are kind of like eigenfunction of this Hamiltonian, and for they have defined something called generalized Jack polynomials, which like it's kind of a double of this one, but with also some cross term. That then the eigenvalue will become like generalized, so-called generalized Jack polynomials. And using that generalized Jack polynomial, they want to show that this term-wise, this equality, like you will just need one of this and with a generalized J inside. And because one generalized J is effectively 2J, then they could like kind of like want to prove this for general beta. But of course, there are a lot more to be done because they need to derive that make the definition more like rigorously, and also they need to have this formula. So that's one of the way we are like now doing. We want to try to find the way of doing this proof.
So this Hamiltonian is
sorry.
does
This one, yeah.
Can be written as some curve, like an algebraic curve. Connected with your Seiberg-Witten.
For not directly this one, but for it's if you go from the Nikolov potential function, this right in the first instructions, like it starts from here, it links to the prime-potential here, right? You have this prime-potential of the Seiberg theory, like this f is like taking this log of this partition, and then from this gauge theory side, you will have some curve, but maybe not directly linked to the I don't know the paradox of land. And also, right, so this is for the 4D beta is one case, and later, then while we are trying to prove the general beta case, we found another way, another approach may be easier. That is like if we leap to 5D case, but still for beta is one, because for 5D case, like things are similar. It's just like you have one more parameter. So interestingly, we found that it indeed could be done. But that's one obstacle that like for 4D case, they have this formula proved by mathematicians. But for 5D case, what we need to do first, like we need the Schur polynomials to also to be kind of like a Selberg integral to be kind of modified, and also like this deformation. Right, we need the q-deformed Selberg algebra. A Selberg integral of their integrand, and we need to prove the new formula. So in the beginning, we followed my old approach like 13 years ago. Like we use a conjecture first and submitted that to archive, and then submitted to Zhang. But during the review, actually the first review just came back very easily. They said like you just add two more references, then it could be published. But when we receive that comment from the referee, we actually already found that for the Faraday case, we could also prove this kind of equation by ourselves. So actually, we took 3 more weeks, and then very happily we found that like for the Faraday case, we could also like have a similar stuff, and we found a formula that first we define this q-deformed Selberg integral, and then we like proposed this Faraday integral, this kind of formula, and then this is proved. And with this proved, like we could easily show something. It looks similar, but still like very non-trivial when you do that. Anyway, so then the Faraday case now is also like fully proved rigorously. So actually, we indeed have a new formula by ourselves. So the next step, we are trying to do the general beta case. So that's basically the story for the our work on AGT conjecture for now. Okay, so for the next stage, then maybe we talk about something more interesting for the guests. So I was also like working on this kind of gravitational wave study for my last postdoc in Taiwan province, because like mainly first reason why we're working on this like from like 2016, or actually the first observation is like in 2015 in the November. So they have like 2 black holes merging, and then you have like this kind of gravitational wave encounter. And we know that could be a way like to have new physics, because like right, it's you could actually there are many events afterwards, like so those like how to raise this like this like 2 black holes merging into a new one. So this vertical line is like their masses, and this horizontal line don't have much meaning. It's just made it symmetric. So in general, like we have this like these blue ones are the observed black holes, like and also this kind of purple or like a purple red one, they are like observed traditionally by electromagnetic waves and for example optics lens or some other X-ray stuff, right? So you see like this this kind of gravitational waves observation is very efficient because like they are just several years you have so many, maybe like a kind of 100 events something. And also besides black holes, they could have some more observations about this kind of neutron star. The neutron stars like for neutron star events not that many, because like they are too small, and maybe and also the frequencies are not matching so well with ground observation, and also because their masses are small, so their signal is weak. But still, like we have several events, like these kind of orange ones are those kind of neutron star events, and usually 2 neutron star merging into a new usually a black hole. And also there are already many other events like observed traditionally, because neutron stars are easier to observe, and usually they are pulsars. When they rotate very fast, it gives you many radio waves, so that's easier to observe. But still, like they are very powerful for this kind of events. Why? Because like yeah, maybe I can say it now. It's like or maybe later. I just should tell you later that like the gravitational waves, even one event will be very important. And then the other thing you could observe from this picture is like there seems to be a gap here. This is called the lower mass gap. It's in general, it's more or less from like 2.5 solar masses to 5 solar masses. Why there's a gap here is like there's some interesting thing about the neutron stars. Like until now we still don't have a study of the equilibrium states of neutron stars, or we don't know much of the exact what the inside structure of this neutron star. So now for the observation, or to our current theory, the observations most massive neutron star is around 2.1 solar masses. And by the theory of the you add rotations or something, maybe at most you could have like 2.6 or 2.7 solar masses, but not more. But of course, like maybe you have known that there's some neutron pressure or something like called like the for between neutron stars and also the white dwarf, like you have this electrons electrons is forming pressure. But for the neutron pressure, is the limit is actually quite high. It's something like 3.3 solar masses. So it's not a real limit for the neutron star. And also for black holes, like for traditionally, if a black hole is formed like by stars, in general, its mass is kind of bigger than 5 solar masses. But that's not a fixed theory because like some cases you indeed have smaller ones, but in general it's like higher than 5. So if you have an event between this 2.5 and 5, you will have to clarify like what kind of star it is. Is it a neutron star or like a black hole? Of course, for black holes, like there are many other possibilities. For example, like you say it's a primordial black hole which is formed from the early universe time. That's possible because like, you could have all kind of different masses, including the supermassive ones inside the galaxy, like millions of solar masses, and there could be very small and very big ones. But of course, like the population of this kind of black holes are interesting to constrain your theory. And actually, there's another window you cannot see here. The other window is like called the higher solar mass. It's like here is like 100 solar masses and this is 80. So the higher solar mass, the higher mass gap. Higher mass gap is supposed to be something still like not fixed theory, maybe something bigger than 80 to 150 solar masses for black holes. Because like traditionally for the astrophysics view, like the black holes formed from stars are not to have masses between 80 and 150. For the otherwise it will be not be formed into black holes. So in that case, like we actually could see like many events are actually inside this range. But I'm not talking about those after merger. After merger, you know how it comes because like for example, this one is something like 90 solar masses, but you know it's like merged between two small ones, so it's okay. But sometimes you have the observation which like in the beginning, you already have some before the merge. One of the like the black hole is already 100 solar masses. So we need to interpret how this comes, how this forms, because like you want to say this is like another star from two star merger, but hello.
So how do you know that it was not formed by other black holes?
Yeah, exactly. Yeah, good question. Because like if you want to say like it comes from two mergers, then consider the time of the age of the universe. The possibility will be very small because you have two mergers, like you have to be close enough. Then like you merge once, then they in the neighborhood maybe not so many other black holes. But if you want to merge twice, it will be like the possibility will be very small. Because like if I am very massive, yeah, I will observe you immediately, and then the nearby there will be no people else. But if I want to merge with another big massive guy, then the possibility is very small. So, of course, that's possible. That's possible. But if there are many of that kind of events, you need to reconsider your story, your possibility. And of course, like there could be also possibilities like primordial black holes with all kind of different masses. And also, there's another possible interpretation that those are neither neutron stars nor black holes. Maybe something we don't know, like a dark star made by dark matter, because like they don't have much constraint on this kind of dark matter theory now. So we could have many possibilities. So right, you could interpret some of those like events in the mass gap to be like dark stars. then you will have some. Of course, that's not so interesting because you also there's a window or there's a constraint. Yeah, there are many papers like like that. But anyway, it's a kind of a possibility that you cannot exclude. Okay. So let's go back. Like let's talk about the black holes. When we want to find the wavelength of this kind of like a black hole merger observation, that the waveform is very important because we know we are not really using a telescope to observe that merger event. It's just like this laser interferometers. So you actually we could only observe this kind of waveform. So it's very important to calculate the possible waveforms before your observation. You need to know like what kind of, if you have two black holes they merge, like what kind of waveforms we are expecting. Then you compare what you theoretically or like numerically derived to your observations. Then you could interpret that's a black hole, not a track nearby, right? So and there are actually in general we make it 3 stages of this kind of black hole mergers or binary star mergers. Like first phase is called in spiral, and this phase is known and also numerically calculation. And then there's a phase of merger, and this is very complicated. Like you could of course do some simulation and try to find some the wavelength. And also the third phase is called rundown, like when they already merged, but then it will gradually like settle down, and then the oscillation will like be damping. And so it's in general this phase, like rundown phase, is like kind of a damped oscillation case. And this is also known, but this waveform could only be calculated numerically. And so how to find this frequently, more efficiently, and more precisely, very important for interpreting the waveform of black holes. So because we are doing theory studies, so that's something we could contribute. And actually, there are some work already done before, like by Italian and Japanese group, like also 3 years ago. Sorry, I did not write down the references of the original paper. It's like by some Hasta and some the group in CISA. Yeah. Sorry. Yeah, Tanzania. Yeah, exactly. Sorry. Yeah, I really should write it down. Yeah. And they okay, so they found like the duality between this kind of this, for example, the duality between short-shelled black hole and this SU2 gauge theory, like for n=2 superradiance gauge theory with like NF-3, and this is exactly the subject we are dealing with for in AGT conjecture. So in that case, like for the short case, like from the matrix, you will find that they satisfy this kind of Ridge-Radar type of equation, and that kind of equation could actually be rewritten in a form after some changing of variables in a form like this. And this is actually in the form of the with poles like 0, 1, infinity, like called the confident Hall equation. And so if you could this equation like in the parameters you have the information with this omega inside, and this is the frequency we want to know. And
what's the phi z? What's the equations 17 described?
Here, yeah, this phi z comes from like this, right? This yeah, come from here, yeah.
So this duality is for any any short directly for D. That's the gauge series is like this particular one is eligible.
All right, for short black holes like this duality.
And as it counts the number of singularities, therefore to say how many singularities and what is the degree of the pole and each singularity. And then change in the black hole will change the point in the Coulomb branch, the masses of the three quarks, and so on. So the parameters of one have very factor.
Thank you.
You want to make the Quasinormal modes of the first black hole.
Yes.
So what is the application of that? You want to use that duality.
Well, why we need the frequency?
Why you need the Quasinormal modes of first black hole?
Sorry. Yeah, I did not say that. Sorry, I forgot one phrase. Like for the rundown case, like when it's like a damped oscillation, and this is governed by this like a Quasinormal mode of black hole.
That's a project written exactly by QAnon.
Yeah. That's the Quasinormal mode of black holes. So if you know the frequency, you will know the waveform. So so here, you could also do the WKB. Yeah. So here, like we do not really solve this equation, but we know that this omega is like is included in this parameter. So we want to know whether we could find a different way to solve this omega. Then it turns out that like and also maybe before that, like right, I did not write down the details here, but say for the superradiance case here, like they will satisfy this, they will have the corresponding Seiberg-Witten code, and that kind of Seiberg-Witten code, like they have some quantized condition, boundary condition, and then that code will also satisfy this point type equation, sometimes confident, sometimes not. But right, we will have a similar equation here, and then we will find the duality between different terms, and you will have dictionary of this omega in terms of this gauge parameters. Then on the gauge side, like we showed before, like it's like written in terms of Nicholas population functions, and then by substituting those kind of parameters inside, we could calculate this omega analytically using this kind of incidental counting. And that does not apply to not only apply to short shadow black hole, but also to curved black holes and many other different black holes. You just need to change the different kind of like a gauge size, like different flavors, and like maybe also like a linear quiver RCU2 or like other combinations. For example, like we could apply that to like also acceleration black holes, and also iron black holes, and also like some other cases.
Say something about extremal ones.
Right, but right. So for the extremal
Black factor, of course, will be
right. For the extreme black holes, like that's interesting because like it's kind of limit of the short shadow or curved black hole case, and then we also take a limit on this side. Then the poles will collide.
That is exactly the case which is not.
It's not interesting about extremal.
Yeah, because they are stable by definition.
Sure,
So you don't need to study the problem of stability.
Yeah, in that sense, yeah.
They are DPS, so stable, and
Right,
you
right.
don't need to work out. If you wish, you can do, but this works for nothing. I mean,
No, it depends what I'm saying, because this is zero temperature solution, of course, and then people can study perturbations around. Not the pure extreme, then you can study
Then
perturbations.
it is not extreme.
You start with extremal ones.
Well, you specialize to near extremality, if you will.
Yes.
It's generally.
If you have black hole, the stationary one, all the example you showed was a static.
Yeah, we could. This is static, but you could also have curved black hole and
Other example you showed were all
or
static.
Like,
yeah. This is yeah. For curved black hole, it's interesting. It's also correspond to this case, but with different diction. And for like this for short shadow curved black holes, they all equal they all link to SU2 and F equals 3, and but with different dictionary. And for the extremal case for short or like extreme curve black hole, like then this ANF goes to 2. We will have like sliding limit for the gate side and also like have a higher pole here. Like it's like you take this kind of limit. Like, and right. I mean, extreme curve. And also like for other cases, like you could also take this kind of a limit back, then go back to structural case, and then it will end up to similar stories. And so actually, I and my friends, like or my friends and I, like we did something on the accelerating black hole first, like to check this Seiberg-Witten duality, and it turns out it works, and that's with my friends like in Suzhou University, like Professor Zhu and Professor Lei in Suzhou University, and also Professor Zhu, who was here before, like
Also start once.
yeah. And right, that's like we have a conference in Shanghai, and that's just there. And right, in that case, like we just say like similarly, we have that case we have 4 regular single points, rather than that it's different as we had the confluent Hall equation before, but now we have just the Hall equation. So we have a similar dictionary, but in that case it's more interesting, like because we found like the quantum pairs, the quantum boundary condition should be considered more regular, more like deeply, because like how you define, how you link your different boundaries is very important. And actually for this accelerating black holes, like there are different kind of this kind of boundaries, and we have to link different boundaries together. And then they yeah, this is like how we like link this take that kind of.
Well, I think regarding your previous question of this Selberg, that's there should be some kind of this, but not known explicitly.
What is not known explicitly?
For the quantum, he was asking like having a special curve behind this project for the point.
Right, so they have this quantum like something curve with something written. And so for right, this like for the this will be that accelerating black holes are also called symmetric. So symmetric, and it's linked to the SU2 gate theory with NF is 4 flavor, and then we have some similar cases. But also like we have different boundaries, so we need to link different boundaries together. Then we need something called a connection formula, like linking different limits, like to the infinity or to the horizon, and then in all different horizons. So this time by using this, like we could like indeed reproduce this kind of data, which is very comparable, very similar to the numerical data known before. And this is like done by like incidental calculations. So that's indeed works. Okay, and somehow this works faster. And then actually at the same time, like I was also considering like the superradiance with my colleagues in Shanghai University, because actually in the story actually in the beginning, like the Professor Schur, like he was a narrator, and he heard about this talk on this supplemental duality, and then he asked me like whether I'm working on gravitational waves, whether we could do something like that. So first, like we have this on symmetric study, and then like at the same time, I think like this could be applied to something else, like superradiance, because like the superradiance case, it also have some similar formula, also constant Hall computation. And the so-called superradiance, like it's like when you have a black hole rotating fast, it will in some theoretically it may induce some new particles unknown, it's like new bosons, like which will be excited by this kind of rotation. So this is called super, and that rotation will like reduce the power of the energy of this rotating black hole, and it's kind of like a superradiance case. So this is called the superradiance for like a black holes. So it's like generally you will have ultra large bosons around your black holes be generated, and that will exhaust the energy of this kind of fast rotating black holes. Okay, and so it's actually the waveform will be similar to a gigantic like hydrogen atom in the universe, like because around it's also like they satisfy this Klein-Gaussian equation, and they for the scalar boson equation satisfy this, and then this very similar to the hydrogen atom. So in that case, like they could be like governed by this kind of also this constant Hahn type equation, and also equals to -3. So similarly, we could do that story, and also we need the help of a connection formula to check different boundaries. And then, but in that case, the precision is kind of not that high. So indeed, we end up with some results like first, of course, we could check the original results for like before, like the Schwarzschild case and the Kerr case. That's okay. And then for the superradiance case, like we could check some of the points like which is derived before. And if we really want to check with the numerical method, the precision is not that high in that case, but the important thing is that like the sign change of this like imaginary part is important, because it determines like whether you have like a superradiance or not. So at least like we have like the input in that case like around this kind of value, we will have a sign change here. So it will show you that the superradiance occurs. And why the accuracy is lower than before in that case, mainly because like for the real part, this is like a similar level, but for this time for the superradiance case, the imaginary part is extremely small. So the accuracy, if we still have like a lower instanton, we only have 5 instanton calculation. So like the accuracy is not that high.
Consider the extreme.
We did not consider extreme case. Yeah. Maybe we could try. Yeah. Okay. Yeah. Thank you. Sure. Yeah. Thank you. Anyway, so this we observe sign change here at the more or less the similar level up from nothing. So still it's like it's a story. We want to improve that. And now, of course, for this continuing work on this one, we are more interested in like in so-called like a Proca case. Proca case like it's like for here we are considering like the boson case like it's easy even for the numerical calculation, and scalar boson. I mean, if we want to consider like a vector boson, then like it will be more difficult. And actually, even on the astrophysics side, it's difficult thing to do, because the separation of Proca equation is only done in 2019, like 5 years ago. So, and but for this duality, we find that it could be done similarly, because like we will have more poles, 2 more poles, but that will not be Hahn equation, but some generalized Hahn equation, and actually I think that will be linked to the linear quiver of this gauge side. Okay. Okay, maybe it's already time, but I want to maybe 2 or 3 minutes. I will give a brief introduction for the neutron status. Sorry for that. Okay, so for the neutron star, maybe why the equation state is important is because like we want to know the non-perturbative behavior of these neutrons, right, in hydrogen state. So by observation we could, sorry, they're all in Chinese, but you could see the picture later. As long as we have equilibrium states, then we could find the mass, the relation between the mass and the radius of neutron stars. This curve means different kind of neutron stars. each point stands for a neutron star. For example, a possible neutron star, like for standard neutron star, have a mass like 1.4 solar masses and with some radius around like 12 kilometers. And so as long as you know the equation state, you could know every neutron star with the correspondence between the masses and the radius. So that means, on the contrary, if we could measure the by observation, we could measure their masses and radius exactly or like very precisely. We could fix this term by fix this curve by observation or have very small windows. But it is actually easy to it is easy to measure the mass of pulsars. For example, you have a constraint here, but you see like there's only constraint on the masses, but not on the radius, because it's very difficult to measure the neutron star radius because it's so small and it's hardly emits anything, and it's so far away. So we only have a very large window for radius before. We only have from this kind of X-ray observation and thermal calculations. So usually the window is like several kilometers. So actually you could draw a lot of curves, a lot of possible curves, and those all are like phenomenologically. This is one drawn by SL4, but this kind of extreme state, we have like more than 100 possibility. So why they so as we said, like the window was very big, but in the observation of this kind of this gravitational wave observation, they have another thing that could be measured. One is called the masses. The other is called tidal love number. It's a tidal deformation of neutron stars. So although this is like a very high correction, but it could be indeed observed by this gravitational wave studies. So that means like the tidal deformability could be observed by gravitational wave studies, and actually similarly, that tidal deformability could be calculated theoretically as long as you have this kind of equilibrium states. So on the contrary, if we could observe this, we know the tidal love number. We could have very small window for this kind of equilibrium states. So even the first events has already ruled out half of the possible equilibrium states candidates. So that means like the gravitational waves, they could measure the radius, or you say measure the tidal deformability very precisely. That is very powerful. That could you just have a range from here to here, and that's different curve to draw by different equilibrium states, and even the first event ruled out half of them. So it's very powerful. And for now, we have like maybe like a 3 or 3.5 neutron star events, but not as good as the first one. Only the first two ones like have good constraints. So, but anyway, it's very useful. So, but still, we want to know what we want to theoretically derive this kind of equilibrium states. So we just start from this kind of ADS-QCD method, and called one of them called cyclic schematic model. And we start from this Bruin construction. And the good thing is that in that case, we will only have one adjustable parameter compared to the phenomenological ones. They have a long list of parameters, maybe thousands, hundreds. But we only have one parameter, the distance between different Bruins. But in this case, like first we can consider this point-like case, and then we end up with a kind of result, but not that good. We could not recover the two solar masses if we want to satisfy the constraint. Then later we move to the this year we move to the incentive gas case, and the highest mass is lifted to this 1.87, but still not good enough. It's still like it's something. It's theoretically derived, and it only have one parameter. Anyway, it's useful, but we need further studies because like it's very useful, very important for the gravitational wave study. Right. Okay, there's something about dark star, but I will start stop here. Maybe you should invite me next time so that I could continue my story. Thank you very much.
Okay, any further questions?
So if there are no questions, we can stop here and you are welcome to ask. We can have discussions.
So if I have one question.
Yeah, let's test the figure again.
Thank you.
Those Iranian modes found that same design of the imaginary part.
Right, that's
They are including
right. So between the Gary mode and damping mode. Right.
so they are near the extremal ones. Would you consider them near extremal?
Right, I have I think maybe it will be similar for the external case problem. We haven't done that. Maybe it will simplify it.
Because it was almost zero, near zero the imaginary part for a while.
Right. Because we will check whether it should be either if we have larger imaginary part, maybe more accurate.
So what about this Quasinormal mode? You said the vector field much harder. What about spinor?
Spinors.
We have electrons and photons, so I guess you want to do electrons and photons. That's what.
Yeah, right. For now, it's like mainly it's a story about photon, but for formulas, maybe on the spinor like I don't know, in general, formulas will be more difficult. Maybe you check the literature, but
Well, yes, the vector photons are also very difficult.
yes. We are concerned with photons.
But if you are looking at just the flashing vector, maybe not that good thing.
Yeah, the problem is that we need to start to rotate to generate the superradiance.
Oh, it's possible.
Yeah.
You can also
Yeah.
that's right. Right. They are used to